Okay, so that is a basic assumption that we had earlier. Right, so we are going to assume that the expected value of y given x is linear, right. So that is essentially what this is telling us, right. So f of x is, so here is the expected value of y, right. There is some kind of a noise corrupted training data that is given to you, but the expected value of y given x is linear, right. And yeah, so we had this discussion earlier. So the nice thing is linear regression is not as weak as you think, right. So x can be a variety of different things, right. X need not just be real valued inputs, right. X need, I mean, they are assumed to be drawn from RP, right. X are assumed to be drawn from some p dimensional real valued space, but they did not just be real valued inputs, they could be any kind of encoding, right. We talked about basis expansions. Right, we talked about basis expansion, which essentially is right, blowing up your input space by some kind of transformation of the input variables, right. So if my original data is x1 to xp, I can think of, right, that this as my input. So that is basically basis expansion, right. I could also think of interaction terms, right. I could think of more complex transformations, right. Sorry. X could be qualitative inputs as well. What do I mean by that? Hot, cold, right? Tall, short, medium height. How would I handle that? If my X has levels in the input, right? Or it could be just red, blue, green. I mean, that does not really correspond to any level, right? I mean, young and old, you can think of saying, okay, young is 1 and old is 2 and middle age is 1.5 or whatever, right. But what about red, blue and green, things like that? Huh? Encode each color, right. Encoding, how do you do the encoding? Yeah, you are right, you have to do some kind of encoding. How do you do the encoding? See, as soon as you said identify yourself and talk, nobody talks.
You put some binary encoding.
I could do some kind of binary encoding, right. So I can think of saying that, okay, I have 4 colors, right. So I will have 2 bits to encode the 4 colors, right. 2 bit 4 gets translated into 2 bits. It turns out that that is usually too much of a compression in the encoding, right. And if you have 4 possible values this thing can take, it is better to sometimes use 4 bits, right. So it is sometimes called 1 of n encoding, right. So only one of those 4 bits will be 1 for any input, right. So red means the first bit will be 1, blue means the second bit will be 1, and so on and so forth, right. Or sometimes it is called 1 hot encoding. So this one of the inputs will be hot, the others will all be cold, right. So sometimes called 1 of n or 1 hot encoding. So you could take care of qualitative inputs like that, categorical inputs also you could do that. And whatever you do, right, I mean, however you have expanded your basis or however you have encoded the thing, finally the model you fit will be linear. It's except that if your original dimension was 1 in this case, right, I had a 1 color input, it could take 4 values. Now my input dimension have become 4, right. And similarly I had p inputs earlier, now my input dimensions has become, in this case, depends on whether I am feeding in x1 to xp also, right. If I only feed in the second order terms, it will still p, but the class of functions I can model is restricted, And if I feed in x1 to xp as well as the squares, then it is 2p and the class of functions I can model has become larger. Okay. So that is basically the underlying setup, right. The model is still linear.
Why is a 4-bit encoding instead of 2-bit encoding?
What's that?
Why is a 4-bit encoding instead of 2-bit encoding?
4-bit encoding is better than 2-bit encoding, is it? Okay. The point is, so when I have 2 bits encoding, so there will be the same input variable that gets activated for 2 different colors, right. Suppose I am using red is 0 1, okay, and blue is 1 1, okay. So that 1 will get activated for both red and blue, and likewise when there is 1 0 and 1 1, right. So the same bit gets activated for multiple inputs, okay, and that gives you some amount of interference in the training, right. You can still train it with 2 bits, okay. You probably need a lot more training data to take care of the interference from one to the other, right. When you have these kinds of 4 bits, essentially you have independent weights modeling the influence of each of the levels. So red, there is one weight, by weight I mean one beta here, okay. For red there will be one beta that will be modeling the effect of red, for blue there will be another beta modeling the effect of blue, right. That way there will not be much interference between the variables, right. So technically you can model it with 2 bits and get away with it, right. It's just that you will probably need more data for the estimation. That's why I said in practice 4 bits is better, okay. Yeah, let's go and continue looking at this. So I am my training data, so fonts are fine, okay. So the training data is I am going to assume is of the form and that each xi okay, right. I am going to assume that I have n data points, each of the form x1 y1 to xn yn, right, and the way we are going to fit this is using least squares. So I am going to translate this into matrix notation to show you some things, right, and in matrix notation when I write x, okay, at least for today, okay, it is n cross p plus 1 matrix where the first column is all ones. So we have seen this already. So it is n cross p matrix where the first column is all ones, okay. So I can write it like this in matrix form. If you think about it, that squared thingy there becomes this, because f of x now becomes just x beta. Okay. What would that be? Since you all done the linear algebra tutorial, you should be able to tell me what that is. Huh?
X transpose.
So I am going to let you, if you can't see that immediately, I am going to let you work it out yourself, okay. And you should get really familiar with doing this kind of derivatives of matrices, okay, because we will be using this quite often. Whenever we write this kinds of error functions in terms of matrices, derivatives, we will use this. You can intuitively see it is right, but you just need to work out the math here. And so at least this seems easy enough. So I am taking the derivative of this with respect to beta, and the only term where beta appears is x transpose x, okay, right. So if x has full column rank, okay, x transpose x will be positive definite, okay. So it will certainly be invertible, okay. So it will be, and no, it is not just invertible, it will be positive definite, and therefore we can assume that it is a maxima or minima. Huh? Anyway, so if I equate this to 0, I will get an extremum point, right. I will get either a maximum or a minimum, okay. So what will it be? Anyway, think about it. I am going to anyway minimize the error, that should give you a clue, okay. Right, so I am essentially have to set this to 0, right, if I want to find the minima of the error, and this is going to give me right. These are all standards. If you already know what the solution of linear regression is, we saw that in the last class, and you should have revised things by now, right. Didn't I tell you that if you read in the previous, whatever we have covered till the previous class and come the next class will be easier, right. So we already seen the solution, right, and so if I put this together, I basically get y hat equal to x times x transpose x inverse x transpose y, okay. So this expression is sometimes called the hat matrix. You know why? It takes y and puts a hat on it, right. So it is called the hat matrix. So hat essentially means what? It is a shorthand for estimates, okay. Hats are shorthands for estimates, denotes that it is not the true quantity. So y is the true random variable, and y hat is an estimate of the value of y, okay. So this is essentially the estimator matrix, right. So in that sense you can think of it as a hat matrix, okay. So another way of thinking about it is the following, right. So what can we say about y, right, the vector y, not the output random variable y, I am talking about the vector y, right. I should say that. So x is n cross p plus 1, what about y? N cross 1, right. So y is actually a point in right, it's n cross 1, right. So, you can take the p plus 1 columns of x, right. So, x is going to have p plus 1 columns, right. You can take the p plus 1 columns of x as a set of basis vectors, right. So, what is the dimensionality of each column? N. Okay. So, each column is a Rn, is a vector in Rn, right, and I have p plus 1 such vectors in Rn. Okay. Now, I can think of these vectors as a set of basis vectors, right. Right. So, ideally I would like them to span a p plus 1 dimensional subspace of Rn. Okay. Here is where all the linear algebra tutorial is supposed to have helped. So you have a p plus 1 subspace of Rn. Okay. Your x beta is what? Will be a point in that p plus 1 subspace, p plus 1 dimensional subspace, right, because x are my basis vectors, right, and I am combining the basis vectors by some set of scalars beta, right, beta 1, beta 2, right, beta naught, beta 1, beta 2, right, that all those scalars are just I am getting a linear combination of my basis vectors. So, it is going to give me some point in the p plus 1 dimensional space, right. In fact, if I am doing linear regression, all I can do is express a point in that p plus 1 dimensional space, right. If I take the columns of my x matrix, okay, any output that I can learn will be a point in that p plus 1 dimensional space. Make sense, right. So, what is the best possible point in that p plus 1 dimensional space that I can predict? So, let us say I have two vectors x1 and x2, these are not the data points, okay, these are the column vectors, okay. So, essentially there are two vectors here, so x1 and x2, right, and this is the space, and suppose I have a vector y which is in the n dimensional space, okay. I have a vector y in the n dimensional space. What is the best prediction I can make? So, y is in R3. I mean, if you can buy into my drawing skills, okay. So, x1 and x2 span a 2 dimensional subspace of R3, right, and y is a point in R3, right. So that is where y is, okay. What is the best prediction that I can make that fits in to the x1 x2 space? The projection of y, right. That is what y hat should be, and will I be able to make that prediction? Am I making that prediction? Yes, because if you look at the error, so y minus y hat is essentially orthogonal to the space spanned by x. So, that is what our minimization condition is telling us, right. X transpose y minus x beta is 0, right. So, essentially it is telling us that, okay, this vector, this is y minus y hat, this vector is orthogonal to the plane spanned by x, okay. So, that is essentially what the minimizing condition is telling us, okay. So, this is the best possible estimate that you can make for y, given that you are restricted to the plane spanned by the columns of x, okay. Does that make sense? So, this is a geometric interpretation of what linear regression is doing, and this also lets us think about some other things, right. So, what happens if x is not full rank? That would mean that some of the columns are dependent on each other, right, or linearly dependent on each other. So, it essentially means that it is not really spanning a p plus 1 dimensional space, it is spanning a smaller subspace, right, it is spanning a smaller dimensional subspace, therefore, your approximation is going to be worse, okay, that is one part of it. Then anything else? Huh? The formula won't be valid. So, we will have to think of different ways of doing it, right. So that is the next thing, but still regardless of that, the best fit that you can get will still be the projection of your y onto the space spanned by the x's. Okay. You have to come up with different ways of finding it, but it will still be the projection, right. So that is the thing. So one of the easiest way of doing it is what? Now we know
Find the independent vectors.
exactly. Now we know that it is just the space that is spanned by these vectors that is important, right, and we are supposed to find the projection onto the space, and if there are redundant vectors that do not help us define the space, we can throw them out, right. Even though I have all these p+1 dimensions, right, whatever is redundant that is not helping me define the subspace, I can throw them out. So there are some very simple checks that you can do, right. In fact, if you use some standard tools like R and you are trying to do linear regression, okay, unless you explicitly tell it not to, it will automatically do the check for you. Okay, it will automatically do the check and throw out the independent columns. It will pick some set of independent bases and then use that to figure out what the projection should be. Okay, great. So what about the case if the number of dimensions is much larger than the number of data points? Do you think that will happen? Yes, no? Yes. Possible. Okay. How many of you here work with images or have done any work with image data? Okay. So more often than not that is the case, right. So because image data is very high dimensional, right, and unless you are able to generate huge volumes of such data, more often than not p will be greater than n. So you will have to think of some kind of regularizing the fit so that you get actually a valid answer, right. If p is larger, so essentially what it means that you have a much larger space and y actually exists in a smaller space than what is given to you. So we have to figure out a way of regularizing the problems so that adding additional constraints on what kind of projections you are looking for, because otherwise it does not make sense to talk about the projection of y on the p+1 dimensional space. Okay.